Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 11, the graph of a function. Classwork. Excuse me. In Model 1, you graphed equations such as y equals 10 minus 4x by plotting the points in the Cartesian plane by picking x values and then using the equation to find the y value for each x value. The number of ordered pairs you plotted to get the general shape of the graph depended on the type of equation, linear, quadratic, etc. The graph of the equation was then a representation of the solution set, which could be described using set notation. In this lesson, we extend the set notation slightly to describe the graph of a function. In doing so, we explain a way to think about set notation for the graph of a function that mimics the instructions a tablet or laptop might perform to draw a graph on its screen. Exploratory Challenge 1. Computer programs are essentially instructions to computers on what to do when the user, you, make a request. For example, when you type a letter on your smartphone, the smartphone follows a specified set of instructions to draw that letter on the screen and record it in memory as part of an email, for example. One of the simplest types of instructions a computer can perform is a for next loop. Below is a code for a program that prints the first 5 powers of 2. Okay, so this first line says declare x integer. So that specifies the domain of the variable x to be the set of integers. Which means the variable can only take on integer values and cannot take on values such as 1/3 or a square root of 2. Okay? Now this says for all x from 1 to 5. Okay, so that's for the instructions between for and next are performed for the value x equals 1, which in this case is just to print 2. Okay? So this line here performs the instructions in the loop body first for x equals 1, then 2, then 3, then 4, then 5. Starting at 1, ending at 5, and just integers. The next line says print 2 to the x. And then the print 2 to the x, that is what's called the loop body. And then it says next x. Okay, so then it says the next x. Substitutes the next element in the set for x and runs the loop body instructions for that value x. For example, if the loop just completed for x equals 3, the next x the computer to run, the next x tells the computer to run the loop body instructions for x equals 4, and then it would tell it to do x equals 5. And then it would stop because the loop is over. It started at 1 and it's supposed to stop at 5. So the output of the program code is 2, 4, 8, 16, 32. So what it did was plugged in x equals 1, 2 to the 1 is 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16, and 2 to the fifth is 32. So here's a description of the instructions. First, x is quantified as an integer, which means the variable can only take on integer values. It cannot take on values like 1/3 or square root of 2, which I've already said. The for statement begins the loop starting with x equals 1. The instructions between for and next are performed for the value x equals 1, which in this case is just to print 2. That's the output. Print means print to the computer screen. Then the computer performs the instructions again for the next x, x equals 2. That is print 4, the output, or the f of x. And so on until the computer performs the instructions for x equals 5, that is print 32. Okay, on to page 2. Exercise 1. That means pause the video, try it yourself, and come back and check your answers. Perform the instructions in the following programming code as if you were a computer and your paper was the computer screen. Declare x integer. Okay, so that tells the computer the domain has to be integers for all those x's from 2 to 8. So we're going to input 2, 3, 4, 5, 6, 7, and 8 into the function, and it's going to tell it to print 2 times that x that was put into it, and then it says do the next x after printing that. So here's the answers. The computer's going to take 2 and substitute it into this. 2 times 2 is 4, plus 3 is 7. Next x is 3. 3 times 2 is 6, plus 3 is 9. Next x, 4. 4 times 2 is 8, plus 3 is 11. Next x, 5. 5 times 2 is 10, plus 3 is 13. Next x, 6. 6 times 2 is 12, plus 3 is 15. Next x, 7. Times 2 is 14, plus 3, 17. Next x, 8. Times 2 is 16, plus 3 is 19. Next x, there is no next x. It would stop. This is what your computer would print. Exploratory Challenge 2 says, we can use almost the same code to build a set. First, we start with a set with 0 elements in it. That is called the empty set. And then we increase the size of the set by appending one new element to it in each for next step. So the computer is going to declare x integer. So we're only going to use integers. Initialize g as the empty set. For all x integers from 2 to 8, append 2x plus 3 to g, print g, and then go on to the next x. So what that's telling the computer to do is take 2, plug it in here. 2 times 2 is 4, plus 3 is 7. And then it created that set with just the number 7 in it. And then it created a set with from the domain of 2 and 3. And then a set from the domain of 2, 3, 4. And then 2, 3, 4, 5. 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7, and finally 2 through 8 inclusive. And this is what it would have printed. So it says, note that G is printed to the screen after each new number is appended. Thus, the output shows how the set was built by adding one element to it each step. Okay, on to page 3, exercise 2. We can also build a set by appending ordered pairs. Perform the instructions in the following programming code as if you were a computer and your paper were a computer screen. The first few are done for you. So here it says declare x to be an integer, initialize g as the empty set, and then for all x's from 2 to 8, append x, our domain, comma, 2x plus 3, our f of x, or y, or range, to the set g. And then next x after it's done, print g. So it did 2 comma 7, 3 comma 9. Now if I plug in a 4, it would look like this. 4 comma, and here's the 4. It put the 4 here and then calculate that. 4 times 2 is 8 plus 3 is 11. So it would give the ordered pair 4 comma 11, print it, and then next g, and then the next x. Okay, and then print that, and so on and so on. So there's 411. And then it's going to take the next x, 5, print the answer, 10 plus 3 is 13. Close the parentheses, it's printed, that's print g. Next x, 6, so it's going to put 6 in my domain. 6 times 2 is 12, plus 3 is 15. And it's going to give me the output, the f of x, 15, comma, and then it's going to substitute in the next x, which is 7. 7 is going to go here, comma, 7 times 2 is 14, plus 3 is 17. Close the parentheses, comma, parentheses, next x, comma, append, or initialize, append, whatever. 8 times 2 is 16, plus 3 is 19. And that is the last. It stops. It closes the set builder notation. And there is our output. Exploratory Challenge 3 says, instead of printing the set G to the screen, we can use another command, plot, to plot the points on the Cartesian plane. Declare x as an integer, initialize G as the empty set. For all x from 2 to 8, append x, comma 2x plus 3 to G. Next x, plot G. And the output would be, plugging in 2 to this would be 2 times 2 is 4 plus 3 is 7. So 2, 7, 3, 9, 4, 11, 5, 13, 6, 15, 7, 17, 8, 19. Okay, page 4. In mathematics, the programming code above can be compactly written using set notation as follows. The set of all ordered pairs x, comma, 2x plus 3, such that, that's what that line means, such that x is an integer and x is between 2 and 8. This set notation is an abbreviation for the set of all points x, 2x plus 3, such that x is an integer and x is greater than or equal to 2, less than or equal to 8. Notice how the set of ordered pairs generated by the for next code above. So here's the set. Also satisfies the requirements described by the set of all ordered pairs x, comma 2x plus 3 such that x is an integer between 2 and 8 is for this reason that the set notation of the form, the set type of element such that the condition on each element is sometimes called set builder notation because it can be thought of as building the set just like the for next code. All right. So discussion, it says we can now upgrade our notion of a for next loop by doing a thought experiment. Imagine for a next loop that steps through all real numbers in an interval, not just the integers. No computer can actually do this. Computers can only do a finite number of calculations. But our human brains are far superior to that of any computer, and we can easily imagine what that might look like. Here is some sample code. Declare x to be real. Let f of x equals 2x plus 3. Initialize G as an empty set. And then for all x between 2 and 8, append x, comma f of x to G. Next x, plot G. The output of this thought code, since it isn't just integers, but the set of all reals, that's integers and all decimals, fractions, and irrationals in between each integer. And the output would look like a line on the graph, which is pictured below. So the difference between up here, what a computer can do, which is right here, plotting dots, okay, we can actually picture in between infinite number of points in between each dot that it had. They had a dot here at 2, 7 and one at 3, 9, but we know that there's an infinite number of dots in between those two. Okay, that'd be 2, comma 2.0000001, comma 7.00001, and so on, just for example. Okay, page 5, exercise 3. It says plot the function f on the Cartesian plane using the following for next thought code. Declare x to be real. Let f of x equal x squared plus 1. Initialize G as the empty set for all x such that x is between and including -2 and 3. So it's going from -2 to 3. So, and it's set of all real, so we are going to connect the dots. If it just said integers, it would just be plotting the dots. When we graph, we generally plot the integers first and then draw the lines or the connect the dots, not necessarily lines because they might not be straight. Okay, so A says to plot the function. So if I start at -2 and put it in here. Negative 2 squared is positive 4 plus 1 is 5. So negative 2 comma 5 is right here. And then I plug in negative 1. Negative 1 squared is positive 1. 1 plus 1 is 2. So negative 1, the output was 2. And then I plug in 0. 0 squared is 0. 0 plus 1 is 1. So at 0, we are at 1. And also keep in mind that in this format, that is our y-intercept. And sure enough, we are on the y-axis right there. And then we go to 1. 1 squared is 1 plus 1 is 2. So it plots the point 1 comma 2. And then we plug in 2. 2 squared is 4 plus 1 is 5. And that would go here at the point 2 comma 5. And then we would plug in 3. 3 squared is 9 plus 1 is 10. And that would go here. And then plug in, and that's it. They said to stop at 3. So there it is. Okay. And then, since it was all reals, then I'm going to connect these. So I come down like so, come around. Okay, and I'm trying to be as neat as possible. It's very difficult drawing on this pad. And there you go. That is about what that would look like. So from negative 2 to 3 on the domain, our range was from 1 to 10. Okay. So now part B says, for each step of the for next loop, what is the input value? And the input value is the number x. So when x was negative 2, we plugged in negative 2. When x was negative 1, we plugged in negative 1. Part C says, for each step of the for next loop, what is the output value? And the output value, if we input x, which is right there, our output is y, or f of x. Or we could say the value of x squared plus 1. That's the output value. Whatever x was squared plus 1. What is the domain of the function f? Okay, so the domain for the function f is the set of all x such that x is between negative 2 and positive 3. And that's what it would look like. This line here means such that. The domain is the set of all x such that, I forgot my x. Let me fix this. This is better. How about that? Negative 2 less than or equal to x less than or equal to 3. E says, what is the range of the function f? So the range of the function is the set of all f of x, or y's, such that the minimum was 1. So f of x is greater than or equal to 1, but less than or equal to, and our highest value was 10. And close the set. Okay, page 6. Closing. The set G built from the for next thought code in exercise 4 can also be compactly written in mathematics using set notation. And here it is. And that is read, the set of all ordered pairs x comma x squared plus 1 such that x is real and it's between negative 2 and 3. When this set is thought of as plotted in the Cartesian plane, it is the same graph. When you see this set notation in the problem set and or future studies, it is helpful to imagine this set builder notation as describing a for next loop. In general, if f maps the domain D onto y as a function with domain D, then its graph is the set of all ordered pairs, the set of all ordered pairs x comma f of x, such that x is in D. Thought of as a geometric figure in the Cartesian coordinate plane, the symbol, that E, simply means in. The statement x is in D is read x in D. Indeed. 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 I'll stop now. Okay, that is the end of lesson 11. Review this lesson summary and go to your problem set.